Let's review what we discussed in lecture 23 with regard to estimation of settlements and something about stresses. If you look at the void ratio versus log of effective stress plot, you find that initially the curve is very flat and becomes steep. The reason it happens is because if the soil is over consolidated, or when you are taken out of the sample, up to the stress it experiences in the field, it will be reloading. That's why you call it CR. You can also call it as CC. It doesn't matter. I mean CS, swelling pressure, swelling coefficient or index. And here you have CC, which gives me the loading for the first time. So obviously when you want to estimate settlements in this region, I have to use this CR or CS. And if I'm using on this range of the stresses beyond PC or the maximum consolidation pressure, please see that maximum pre-consolidation pressure, I have to use CC. So this loading to the right is called virgin consolidation, and to the left is called the reconsolidation or reloading. This is how the real life looks like, and you can see here the slope here is something like 0.4 and the slope here is 0.38, and you can definitely say this is a very small fraction. Okay, here you can see the E log sigma for a particular soil. Initially it is flat, and let us say up to what stress? The maximum consolidation pressure is, past pressure is 900, present stress is 300. So for stress increment from 300 to 900, we use the value of C recovery or reloading, and for stresses beyond 900, we use the value of CC, which is higher. So I can express this mathematically here. I can estimate settlement using simple MV. Settlement is equal to coefficient of volume change into increment in stress into thickness. But the problem here is this MV is not a constant. What we generally say is that I can estimate based on the first part of the settlement and the second part. This is using CR, H into thickness, which is common, CR by 1 plus E naught, log sigma dash C, which is the maximum consolidation stress, here pre-consolidation pressure divided by initial pressure, effective stress, plus CC by 1 plus E naught, log initial plus the increment divided by the maximum consolidation pressure. So it consists of two parts. This is the settlement in the reloading stage. This is the settlement in the virgin loading stage. Another way of looking, if the only settlement is normally consolidated soil, then I have simply thickness 1 by CC by 1 plus E naught into H. This is the CC into log final effective stress minus the initial stress. This is for normally consolidated soil, and if I have only over consolidated in the reloading stage where the final effective stress is less than sigma dash C, as you can see here, then I only have reloading, so I use CR. And if you have over consolidated soil, the final effective stress is greater than the past maximum pressure. As I mentioned, the two components, H naught by 1 plus C naught, CR, the reloading, log maximum consolidation pressure by initial plus CC into final log of final stress divided by the past consolidation pressure. So please remember, when you are estimating settlements, it is very important to find out if the soil is normally consolidated or over consolidated. And I just mentioned with regard to the shear stresses, how we find out the mode failure envelope. I just want to revise here. This is the stress sigma x, tau xy, sigma y, tau yx, and draw the mode circle. You get the principal stresses sigma 1 and sigma 3, and that is how you find out. And in this particular case, tau max is equal to the radius, which is sigma 1 minus sigma 3 by 2. And the center is given by sigma x plus sigma y by 2. So if I define this as P and sigma 1 minus sigma 3 by 2 as Q, we can plot the stress points. And here is the stress path. This is, I increase starting from a sigma 3 a hydrostatic stress, point A is here. You keep on increasing vertical stress, you get more circles of different sizes, and the stress points become A, B, C, D, E, and if I join them, I get the stress path. This is how we defined earlier, and we need this concept in order to study the strain. And here are the 4 quadrants. I start from here. If I increase the vertical stress under a foundation, you have the soil here and you have foundation, you are constructing something, which means the vertical stress is increasing, and because of that the stress path is in the first quadrant. If you say I have a sample in which the soil is moving away, sigma 3 is decreasing, you get what is called an active state. If you have excavation, you are removing the soil, in which case the stress path is in the third quadrant. If you are pushing the wall towards the soil, you are increasing the confining stress, which gives you stress path in the fourth quadrant. These are the 4 different cases, and we try to simulate them in the laboratory, and you can have different stress paths in order to simulate what is happening. And you also will find that in the odometer, it's under K0 condition, which means there is no lateral strain. And you can have, this is K0, and you can have hydrostatic anywhere in between also. Then we also have different states. If I have a long retaining wall embankment, if I have a very long one and look at the cross section, it doesn't matter where you look at it. These kind of problems are called plane strain. Here, what you find here is sigma 1, epsilon 1, sigma 2, epsilon 2, sigma 3, epsilon 3 are the 3 coordinate systems. Because it's a long wall, there's no strain in the longitudinal direction. Whereas you can have all the 3 stresses and they are different, sigma 1, sigma 2, sigma 3. You can have strain in the vertical direction and in one of the lateral directions, but strain in the longitudinal direction. And you can also define what is the stress sigma 2, which is given by Poisson's ratio times sigma 1 plus sigma 3. These problems are called plane strain problems. Axisymmetric are where you have sigma 1, sigma 2, sigma 3, and you have different strains, but what you find here is that axisymmetric, the sigma 2 is equal to sigma 3, and which means epsilon 2 is also equal to epsilon 3. So this is how we do triaxial test. We have vertical stress different from radial stress. So sigma 1 is the vertical stress, sigma 2 and sigma 3 are equal to stresses. Vertical strain is epsilon 1 is major principal strain equal to vertical 1, and the 2 lateral strains are equal to radial strains. If I say that there are no horizontal, no uniaxial, only vertical strain, and these are 0, you get uniaxial compression.